Welcome back, everyone. In this video, I'd like to talk about the Citicorp building. You may have noticed this last weekend that Veritasium dropped a video on this very topic. Links in the description. Definitely go check that out. I highly recommend it. Today, I'd like to talk about some of the numbers and analysis for how this building works and why it didn't. So I'm joined today by Mini Citicorp right here, and the first thing that we'll notice is that there's really two independent structural systems that compose this building. We'll have the central core and the exoskeleton. Now, our central core has one job. It is responsible for carrying half of my gravity loads from the upper 48 stories and all the gravity loads from the lower 10, which composes of just the core here, down to my foundation. Now, it's tied at every level into my exoskeleton system, which does everything else. This system carries 50% of my gravity load and all of my wind load, which is going to be the primary lateral load on this system. So I'd like to talk about first why the unusual shape for this building from an engineering standpoint. Architecturally, we're required to have these side columns and no corner columns going down to the base. And infamously, there are no corner columns anywhere. There's partial column heights, and they're clipped at the top, so it doesn't actually connect. So it would effectively just look like a little freestanding column right there. So why did we do that? It turns out there's a very good reason. If I have 48 stories of continuous column here, that means I have 48 stories of load that can get transferred all the way down the corner of my building and then end up at this unsupported corner right here. That unsupported corner is going to have a very bad time carrying that load horizontally right over to my core system. So rather than transfer 48 stories down here, I'm going to transfer it gradually back to my trunk. So you'll notice it has a very tree-like shape. We have the trunk here at the bottom that extends all the way up. And then each set of branches, which are my chevron braces here, will carry 8 stories of load. So that 8 stories of load gets transferred down my branches and then down the trunk to my foundation. We still have 8 stories of unsupported load right here, which we're going to solve by slapping a big old truss on all 4 sides like that, so that we can carry that load horizontally over and then down. So that's how the gravity on this system works. What we're going to do is we're going to do a deeper dive into the gravity, and then we're going to look into the wind load in a little bit more detail for why having no corner columns is going to be a big problem for us. Now, the first thing that we need to square away is why 50% of the load is carried by the core. So what we're going to do is we're going to draw out our tributary areas. So inside this box is going to be the tributary area for the core. So I'm just drawing a line halfway between my core and my perimeter. And all of that area is then going to get transferred to the core. And if we check it, it actually works out to be exactly 50% of the floor area. So amazing how that works. That's what LeMessurier assumed in design for good reason, and that's what we're going to continue doing right here. Now, we're going to mainly focus on the perimeter system, our exoskeleton, rather than the core. So we'll say our core does great at carrying our 50%, but now we need to divide up our load for the remainder of our columns around the perimeter. So you'll notice there's 16 columns around the perimeter, and there's 2 different sort of classifications that we can have. We can have a corner column here, and if we check the area for that, it's about 1/56th of the total floor area is carried by that corner. And all of the side columns, there's going to be 3 for each side, 2 secondary columns, and the main trunk of our tree will carry 1/28th of my total loading. Now, in addition to the floor load, my exterior columns that are part of my exoskeleton will also carry cladding. So that's essentially the wall on the exterior part of the building. And we'll notice that because there's 16 columns, all of them will carry an equal amount of cladding around the structure. Now let's go ahead and calculate some of our loads. So I'm going to start with some of the corner loads here. That's going to be acting on these corners of the building all the way down. And we'll start with the floor load. I've assumed a load of 60 pounds per square foot. That accounts for all the structural steel, the decking, the concrete, and acoustical tile, and everything else like that. So if we check Diane Hartley's thesis, she actually calculated this to be 61 pounds per square foot, and I'm going to round that off to a nice 60 pounds per square foot. So that's where that number's coming from. And now we need to find the area that's carried by each of these corner loads. Well, that's 1/56th of my floor area. Each floor has an area of 24,600 square feet. That's a lot of square footage. And we're going to need to multiply it by 8 stories because each of these stacks, if you will, has 8 stories in it. So therefore, my total square footage is 3,514 square feet. And multiplying that by 60 pounds per square foot, we'll find that this is 211 kips. We can do the same thing for the cladding, only all of my columns on the exterior carry 1/16th of my building perimeter. So 1/16th, my building perimeter is 627.3 feet. And then I need to multiply that by the height. So this height right here is going to be 102 feet for each stack. So therefore, I have 102 feet times the perimeter. That gets me an area of my wall. And then 1/16th of that goes into my corner. So this is a square 4,000 square feet, which works out to be 80 kips. And that number is being multiplied by 20 PSF in this case, which again is a average number for a typical aluminum and glass cladding for this kind of building. All right, you'll notice there's some more corner loads here for the crown. Those are the loads coming in from the top right here. Now, rather than waste your time with this, that includes the tuned mass damper, the walls up there, there's floors up there, there's a roof system up there, there's a whole bunch of stuff going on up there. But it all works pretty much the same way, and so we found that to be 156 kips of load on each of the corners. Now we can repeat this for the perimeter. So on the perimeter columns, that's going to be 3 here, and let me move that slightly. So these ones are going to frame in right there, and we'll also have one here, here, and so on. So each of those represents an 8-story stack of loads from the perimeter. So the perimeter area is 1/28th of my floor, and so that's the same 24,600 square feet times 8 stories. So this is obviously twice what we had for the corner, so that's 7,028 square feet. And multiplying that out by the 60 PSF, we find that this is 422 kips. And lastly, the cladding, I'm not going to repeat myself, they are the same. All columns carry 1/16th of the load, so this is also going to be 80 kips right here. Lastly, we do have some crown loads here, here, and here along the perimeter. And that, once again, includes my tuned mass damper and other things within the crown of the building, which adds up to 238 kips. So combining loads, I want to consider a typical chevron example. So we'll just pull out this chevron right here, and we'll draw it scaled up just a little bit. And so this is going to carry a corner load, and really it's half of a corner load, because the other half of that corner load is going to go down the other side of my building down here. And then we'll also have a perimeter load framing in right here. Now, this at the base is going to be supported by my reaction right down here. And so if I want to analyze what the axial force in this brace is, first I need to find its angle. So once again, the engineers were really thinking to make our life easy for this. This actually makes a 3, 4, 5 triangle. So this is 3, 4, 5 in terms of the ratio, which means the vertical component is 4/5 or 0.8 of the total load. So therefore, if I want to do equilibrium at the top here, I want to make sure my forces balance in the vertical direction. I'm going to have 1/2 of a corner load is going to have to equal 0.8 of my brace load. And I'm going to call that the top part of my brace, because as we'll notice, my brace is going to immediately get more load in the bottom part. So we can go ahead and solve that. So if I want to find my brace top, it's going to be 1/2 of the corner load, which is 292 kips from what we found before. We're going to divide that by 0.8. and we find that this is 182 kips. Nice. So that's the demand in the top part of my brace. Moving down to the lower part of my brace, we'll find that I'm now accumulating an additional perimeter load on that, so the lower part is going to carry a higher amount of gravity load. Now all the angles work out to be the same, and so what we'll do is we'll just say our brace on the bottom is going to be the perimeter load. So the perimeter load was 502 kips. We'll divide that by the same 0.8 factor, and I need to add that to the load that was above it, which we found was 182 kips. So therefore, in the bottom of this brace, I carry 809 kips. So we get a pretty big increase in the axial load as we go down this brace. Now, what's cool about this building is that other than the top one, which carries crown loads, every single brace is exactly the same in terms of the gravity loading. So they all carry one perimeter load like this and half of a corner load. Where the load is going to accumulate is down our central column. So let's take an example. Let's look at this point right in our central column, and we're going to calculate all the loads that get added up to accumulate into that point. So we have these corner loads from the crown. We have 3 perimeter loads from a crown. And I will note also the corner loads, only half of them is going to go to the side of the building because the other half is going to go to the other side of the building. And then we're going to accumulate a whole lot of perimeter loads here. So perimeter load there, 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 and there. Plus there's 2 half perimeter loads up at the top. So each of these is 0.5 apiece. Lastly, we're going to have some corner loads. So I have 1, 2, 3, 4 corner loads. All of that force is getting accumulated right here. So therefore, we have 5,464 kips. So that can get really large. That's 5 million pounds already, and I'm only about halfway down my building. So if we want to wrap all this up, all the box numbers here are my chevrons, and they all carry the same load going down, where it carries a small gravity load in the top and a big gravity load in the bottom. And the loads here on the side are my column loads, and you can see as they increase going down the structure until I get about 12 million pounds of load there at the base of each of these columns. Now, this is the dead load only, so I'm only looking at self-weight. You can do similar exercises for the live load. I'm not going to get into that here. It looks pretty much the same. It's an office building, so you could probably assume about a 50 pounds per square foot live load everywhere, and you don't have to worry about cladding because generally speaking, we don't have live loads on the cladding. Now that we have a grasp of our gravity loads, let's take a look at the lateral loads on this building. So let's say I have wind load coming in from this direction. That's going to move all of my stories that way, which means this is going to have to get shorter. So it's going to get compressed, and this is going to have to get longer, which is going to be put into tension. So let's focus on this compression side. The same thing happens on the tension side. You just reverse the directions. So right here, this brace is going to put a force on the joint. By being compressed, it's pushing back on it. So it's going to push up and to the right. Now, to the right is fine because I have a beam right here that can pull back to the left. However, up is a bit of a challenge because normally that would be in a column pulling down on my structure. However, I don't have that, meaning that upward force has to get countered by a downward force from this brace right here. So a downward force means this brace is pulling on this, which pull means tension. So this side is going to be in tension. This side is going to be in compression. And I'm going to have a set of compression braces going down and a set of tension braces also going down. So now all of my braces are engaged in this system. You'll notice that the tension and compression here kind of balance out. So there's not going to be any force that gets transferred down from that. However, on the sides, I have 2 tensions right here, which is going to have to resolve in a force that gets transferred down this column, kind of like a gravity load, and that's going to accumulate over the entire building. So now that we have somewhat of an idea for how this works, let's do some numbers and get into a little bit more detail. For the lateral load, let's say we have wind going in this direction, and the first thing that we need to do is get rid of all the extra stuff. So obviously there's a lot of floor systems here. We're not going to need any of those, but also this column and this column, which carry gravity load into the brace, turns out we don't need that for a lateral load analysis. So if we have load here and here, each of those being 1/2 of the building shear, then we'll find that this column, and therefore these beams are zero force members, so they do nothing in this analysis. So let's simplify it as such. So once again, we have half that building shear on each side. So the building shear is going to be the total accumulated load above some stories. So if, say, I'm looking at this set of bracing right here, the shear is all the load that's accumulated from above that. And we're also going to have an overturning moment associated with this building, because essentially the building acts as a cantilever, so it's fixed at the base, and therefore we're going to get a moment that's trying to force this thing over. I'm going to draw that a little bit later, but let's keep that one in mind. Now let's draw how the structure is going to deform in tension and compression. So for example, we've seen before that this side and this side are going to be in compression. So I'm going to make my compression red here. So anything that's red is going to be in compression. And we also saw that this side is getting essentially forced down right here. Now, if I look at tension, we're going to have to balance out our compression braces on the sides. And then this entire side on the left is also in tension. This now satisfies our equilibrium. So if we look at, for example, this joint right here, we're going to pull on that joint with this brace, and we're going to push on it with that one. And that push and pull to make sure that our forces balance out in the vertical direction must be equal to each other. So now what I want to do is find out how much force goes to each set of braces. So these two braces right here are going to be carrying 1/2 of V. And if we go back to our triangle for these braces, it was that 3, 4, 5 triangle again. My horizontal component for the brace force is going to be a 0.6 factor. So therefore, we can consider a sum of forces in the horizontal direction for those braces. So that 1/2 of my shear has to equal 2 braces multiplied by the horizontal component of 0.6 times my brace force, which I'm going to call B here. So solving for B, we'll find that B is equal to my shear divided by 2.4. Now, as we discussed before, this component and this component have to be the same because we have to ensure that our sum of forces in the vertical direction always balances out at each of these corners. Therefore, this brace force B is actually carried by all 8 braces. Now, we also have compression and tension in these core columns that I mentioned here. And the reason that happens is because I need to have reaction forces here in my free body diagram. So obviously we're going to have horizontal reactions, and they're going to occur right here and here because that's where the brace forces frame into it. But there's going to be a net compression here, so I need to hold that up, and a net tension here, so I'm going to need to sort of pull that down. And what's going to happen with that is we need to be able to calculate an overturning moment on the building to find those forces. So the distance between those two forces is 152 feet. So if I have some overturning moment on the building, and we'll call it M at any particular location, that M will have to be balanced out by this force and this force. So that means, let's call those forces R. So if this is R and this is R, that means force R is my overturning moment divided by 152 feet. And that's what I'm going to use to find my column forces going down the building for wind load. So our next goal is to find what is this shear and this overturning moment. So let's go ahead and do that. So here's our building. It behaves like a cantilever again, and I'm going to put a distributed load on this thing. So we'll have load going all the way down. I'm not going to put load on the leg here. There is going to be some, but it's going to be pretty minor. So this distributed load, we're going to say it's uniform just to keep our analysis easy here. And let's say it's 35 pounds per square foot. That number is coming from the New York Building Code at the time, which is specifying 35 pounds per square foot as the maximum wind load that you could apply on this building. That wind load is going to be smaller as you go down the building down here, but we're going to overestimate it just a little bit because I'm also not accounting for the load down here. We can multiply that 35 pounds per square foot times the side length of the building, which is 156 feet and 10 inches to find that this is 5.5 kips per foot. And so therefore we need to do a shear and moment diagram for this thing. So the shear diagram is going to look like this. It's going to vary linearly going down the building. And we're going to get about to here where it transitions down and just goes straight down, because at this point I'm going to assume I don't have any load. And the moment diagram is going to be the area under the shear diagram curve, which means it's going to be parabolic. So it's going to take a shape like this. And it peaks out somewhere like that. And so this rapidly grows in magnitude as I go down my structure. So let's go ahead and put some numbers on that. On this next slide, I have that already done for us. And so it's breaking it all down. So essentially what we have is our shear at each level. So if I have a shear at each level, I can take those shear, and we know that my brace force B was V divided by 2.4, and that gets my brace forces. I have compression side braces and tension side braces going down my building. So obviously the lowest braces are carrying the biggest force in this case. If I look at the overturning moment, let's add on to that. So now I'm tacking on my column loads, which are these numbers right here going down. And so those column loads are going to be, my reaction R is M divided by 152 feet. You may notice that this looks kind of small, but it's multiplied by 1,000 here just to make sure that that all works out, because otherwise we have 2,348,000 kip feet for an overturning moment at the base. So it's a huge moment. The other thing that we'll notice is that we're getting pretty big axial forces down here at the bottom. And so if we compare what this does in terms of our combinations of dead and wind load, the dead load was about 12,000 kips at the base of the building, and our wind load is also causing about 11,000 kips of axial force in our base column. So it's a pretty huge amount of load, and it ends up canceling out almost all of my dead load in the column that is taking the wind load. The other thing that we'll notice with this is as I go down my building, of course, my forces on the chevrons gets bigger from wind, but again, it stayed the same going down the building for dead load. So again, these are getting more and more load as I go down that building. And this represents what would have essentially been the design for the building. So this was sort of our load combination that we'd have. We didn't worry about any other types of wind load, hint, hint, getting into that diagonal or quartering wind case. And so we would design essentially our braces for these tension forces here, and then compression forces on this side right here. And then our columns could be able to carry this largest compressive load right here. Now, these braces are actually multi-part systems, so they're about 120 feet long, and so they were actually spliced along their length. And so that's a lot of the times the bolts that they're talking about. There's going to be bolts along this length to keep those braces intact. And generally speaking, those bolts only matter when we're in tension. However, you can see the tension forces in these are relatively small, or so we think. So the compressive forces are generally going to be much larger because it's adding on a compression from wind plus a compression from our dead load. However, what happens if we increase the wind load? So that's what we're going to do here. So we're going to consider the diagonal wind case. So let's look at this now. And let's say I have the top-down view of my building. If I'm looking at a diagonal wind case here, we'll call our wind load W. There's a couple different ways of breaking this down into components. Probably what was done at the time, although this is somewhat uncertain, is that we can break that into essentially a triangle. So I'm not changing my total wind load, but I'm applying, for example, square root of 2 over 2 in this direction, square root of 2 over 2 in this direction. So I'm going to round that off to 0.7 wind in each direction. If you look at modern wind design, we use 0.75 wind in each direction, but let's just go with the 0.7 for now, because that's likely what would have been done at the time. So if we look at each direction individually, so let's look at this wind load going into the page here. We'll have our compression and tension regions here. So we'll have compression, compression, and all this side is compression. And then tension, tension, and then all of this side is tension. And now if we look at wind in the other direction, this is the one we already looked at. So we'll once again have compression, compression, and all this is compression. And we'll have tension, tension, and all three of these are going to be tension. So this is where things get interesting. So now if we look at the diagonal load, so I'm going to put load in this diagonal direction right here. In terms of the columns, I have a tension column, a compression column, and a compression column. The columns don't really interact. So this is going to be tension, tension in my columns, and compression, compression in the columns. So we're seeing column-wise, this building is actually more efficient for the diagonal winds than it was for just the straight-on headwind. So now I've divided my column loads into two columns here rather than focusing it all into a single column. The load, for example, in these columns is also only going to be 70%. So each of the columns is only going to carry 70% of what it did before. And let's get a nicer pen for that. So 70% of what it carried before. However, if I look at the diagonals, my braces, things are going to be a little bit more tricky because this is tension and it's also tension here. So those tensions add together. So I have 0.7 plus 0.7 is going to be a 1.4 of tension right here. So this is now 1.4. And that's going to be problematic. We'll notice the same thing happens in a compression here. So this is now compressive right there. And we'll get a compression on this back one as well. And then a tension on this one right here. The other four, this one right here, for example, tension, compression cancels out. It's 0. There is no load on any of these here, or this one in the back. So summarizing this change to the diagonal wind, if I have my orthogonal wind case on the left here, all these brace numbers I'm going to multiply by 1.4. So 1.4 times my brace becomes my new number. So I got more compression in these braces, more tension in these braces over here. Then looking at my column numbers, which we called R, those are all reduced. So it's 0.7 times my columns. So now let's combine that with dead. And this is where things get interesting because again, we are adding and subtracting things that are pretty similar magnitudes. So if you make a small change in the wind, it can make a very big change in the resulting force. So here's our combinations from before in the dead and wind, but now we're looking at it with the diagonal case here on the right. And what we'll notice is there is a couple of these that have major problems. So the infamous floor 30 right here is about a 250% increase in the demand. So that's going to be major problematic if we design that thing to carry 257 kips and now it carries 683 kips. Those splices in that brace are going to have a very bad time. We'll notice other similarly large increases always in the lower part of the brace. So that's about a 200% increase there within the second stack of braces. The upper parts of the brace tend to have less of an impact just because they carry less gravity load. So this from 1,117 to 1637, that's still going to be bad, but not quite as bad because I already designed that connection to carry a good amount of tension. It's carrying, 500 kips more, but that's only about a 50% increase. So it's not quite as bad as what we're seeing there. Column-wise, obviously we're doing better. My column loads went down with this diagonal wind as we were kind of expecting, but I'm going to have a number of braces here that are going to have major problems. The next thing that we should consider is that right now we just added dead and wind just straight together. In modern design, we have this thing called an overturning combination. So if we look at, for example, LRFD design, we would have a reduced dead load combined with our wind load. And the purpose of that is to increase the moment on structures or increase this likelihood of seeing when this stress changes sign. So when it changes from compression to tension, we're going to be better at detecting and designing for that. Well, if we look at the ANSI A58 of the time, so this was from 1972, we'll notice that there is no reduction ever in a dead load. But you don't really consider it. But there is a little caveat, and I love these caveats in the code, where they say dead load counteracting live load. So when loads other than dead counteract dead loads in a structural member or joint, and by the way, that's exactly what we have going on here with our braces, special care shall be exercised by the designer to ensure adequate safety for possible stress reversals. Yeah, so what should we do about that? And it doesn't really give us any guidance. So what I'm going to do is I'm going to adopt what happened in 1998 later on. So in 1998, there was an addition to the allowable stress design load combinations that, we'll just add it down here, 9, that was essentially 0.6 times dead plus wind. That seems like a ridiculously huge reduction in my dead load. The purpose of that, it's a little bit more complicated than just reducing dead load, because it's also trying to increase a wind load effectively at the same time, but doing it with essentially one factor instead of two factors. So that's sort of what it's doing, and that's why it's such a big reduction in dead load. Nobody expects actually 60% of dead load, but that's what they've stated. So if we look at that load combination, what happens? So now we're looking at 60% of this plus 100% of this gets us a new combined load. And on this next slide, I want to compare this now to the original design. So original design for this building, once again, we'll look at the infamous Story 30 first. We designed it for 257 kips. Now it is 4 times as large. So it is now 1,000 kips of demand. There's absolutely no way that any connection that was designed for 257 kips is going to survive a 1,000 kip axial force in this case. And we'll notice that there are also similarly large increases in the axial demands, both in the lower stories there. This one looks like an outrageously huge increase as well. Chances are this one would have been designed for some nominal value. For example, like a minimum design of 250 kips is specified in the design plan. So even though you see a really low value, it was probably designed for something of about 250 kips, but that's still a very large increase of about 2.5 times. Also of interest, we are actually going to start seeing uplift in the columns on this tension side where the wind is hitting. I don't know exactly how that was handled in terms of the design. So it's still doing okay so far. So we'll assume that it is just fine. And that's a wrap. So to make a long story short, yes, strengthening these braces was a very good idea. So thanks to LeMessurier for making that happen. And I hope you learned something from this video. So have a great day, and I will see you next time.